Hi, welcome to a multi-level video. I'm going to explain induction and differentiation. So check out this exercise. It asks me to prove by induction that y equals 1 over 1 minus x. That therefore, the more that I differentiate, we're getting n factorial, depending on how many n times I've differentiated, over 1 minus x to the power of n plus 1. So I have to prove that it works for n equals 1. So that's what I'm doing right now. So dy dx, I'm just differentiating here to what I have on the left. And I get that it's a 1 over 1 minus x. Remember the chain rule, I have to multiply by the derivative of minus x. And in fact, it's true, I do get 1 factorial over 1 minus x up to the power of 1 plus 1, which is 2. So it's all good. It works. Okay. Now, let's take a look for a minute to This is going to look for a minute what we have to assume. We have to assume that it works for n equals k. So that's simply what we're going to do. It's going to seem like a bit stupid because we just keep rewriting it as we found it, but in reality, this is extremely important to do because it allows me to maintain rigor. So I'm going to assume that it works for n equals k, and I'm just rewriting the formula that's up there. And now I have to do the difficult part. This is where the hard work comes in. I need to prove that it works for k plus 1. So let's write that down. I want to prove that differentiation of y k plus 1 times over x is going to give me k plus 1 factorial to the power, over 1 minus x. And now I'm going to get k plus 1 plus 1, which is k plus 2. Did I just write a 1 there? Oh well. It should be k plus 2 in the denominator. So that's what I need to prove. That's what I really need to prove. So let's take a look at how we do it. Well, it's not going to be that complicated, because if you think about it, differentiation k plus 1 times of y over x is simply going to be the differentiation of my assumption, which what we have right on the left of where I'm writing right now. So all I have to do is differentiate that thing that I have over there. So let's do it. Very careful. Chain rule becomes very important here. So times, and I'm just using a property of when I have a function in the denominator, I just have to square it. So I'm going to get minus 1 over the whole thing in the denominator squared, and I have to multiply by the derivative of what's in the denominator. So I'm going to get a k plus 1 because I'm taking that from the exponent in front, and I multiply by 1 minus x, and now k plus 1 minus 1, I'm simply going to get to the power of k. And I still have to multiply times the derivative of what's inside, which is going to be minus 1. So the two minuses is going to cancel each other out, and I'm going to end up with something positive, and I'm going to end up with k factorial times k plus 1 times 1 minus x to the power of k. I just put what I had on the top, what I was multiplying, I just put in the numerator. And at the bottom, I'm going to get that k plus 1 to the power of 2, and that's just going to become 1 minus x, to the power of 2k plus 2. Great, so how do I clear this out? Now, this seems like we're in a bit of a static position. There are two things that can be hard here. First of all, remember how the factorials work. So k factorial times k plus 1 is going to be simply k plus 1 factorial. On the other hand, use exponent rules. When I have the 1 minus x to the power of 2k plus 2, when I have them, how do I break that down? Well, that's just simply going to be 1 minus x to the power of 2k times 1 minus x to the power of 2. Now, the reason why I'm doing this so slowly is to help you realize how this works. Now, 1 minus x to the power of 2k is simply 1 minus x to the power of k times 1 minus x to the power of k. So I can just cancel the 2 with the whole thing on the top. And with the factorial rule I just explained earlier on, I can just rewrite this as k plus 1 factorial over 1 minus x to the power of k plus 2. And hence we did it.